So if you've ever seen a massive container ship or a cruise ship up close, maybe in a port or even just in pictures, you might have noticed something a little weird. Right at the very front, just below where the water hits the hull, there's this giant, bulbous, almost nose-like thing sticking out. For a long time, I just assumed it was, I don't know, some kind of bumper or maybe just a weird design choice, like the ship equivalent of a giant chin. But it turns out this isn't just for looks, it's actually a brilliant piece of engineering with a super important job. That big round protrusion is called a bulbous bow, and it's one of the cleverest fuel-saving hacks in the entire shipping industry. It's all about physics and manipulating the water in a really counterintuitive way. You see, when a huge ship plows through the ocean, it creates a massive wave at its bow, which is basically just wasted energy. The ship has to constantly climb its own wave, which creates a ton of drag. This is where the bulbous bow comes in. It's designed to do something pretty amazing with that wave. And the effect is huge. We're talking about saving millions of dollars in fuel and making these colossal vessels way more efficient. So today, we're going to dive deep, pun definitely intended, into the science of the bulbous bow. We'll look at how it creates its own wave to cancel out the main one, run some experiments to see this in action, and figure out why you see it on giant tankers but not on your buddy's fishing boat. It's a perfect example of how sometimes the weirdest looking designs are actually the most brilliant. Okay, so to understand why a bulbous bow is so genius, we first need to talk about resistance or drag. When a ship moves through the water, it has to push all that water out of the way. A huge part of this resistance comes from the waves the ship itself creates. Think about it as the front of the ship. The bow cuts through the water, it pushes the water up and out, creating a wave. This wave travels along the ship, and the energy used to make that wave is essentially stolen from the ship's engine. The ship is constantly fighting to climb over this hill of water it just made. It's like trying to run on a treadmill that's always going slightly uphill. It's just pure wasted energy. This specific type of drag is called wave-making resistance, and for big, fast ships it's a massive problem. It can account for a huge chunk of the total drag, so engineers a long time ago were thinking, how can we fight this? How can we flatten that wave? And someone came up with a totally backwards sounding but brilliant idea. What if we fight the wave with another wave? This is where the physics gets really cool. It's all based on a principle called wave interference. If you have two waves and you line them up so the peak of one wave meets the trough or the low point of the other wave, they cancel each other out. It's called destructive interference, and that is precisely what the bulbous bow is designed to do. Because it's submerged under the water as the ship moves forward, the bulb creates its own separate wave system that starts just ahead of the main bow wave. The shape, size, and position of the bulb are all meticulously calculated so that the wave it creates is perfectly out of phase with the wave created by the main hull. So the trough of the bulb's wave lines up with the crest of the ship's bow wave, and when they meet, poof, they partially cancel each other out. It's like putting on noise-cancelling headphones, but for water. Instead of one giant energy-sucking wave at the front, you get two smaller, much less powerful waves that work against each other. The result is a much flatter water surface around the bow, which means significantly less wave-making resistance. The ship no longer has to waste a ton of energy climbing its own wave. It can just slice through the water much more smoothly. This effect is most dramatic at the specific speed the ship was designed for, which is why these bows are so carefully engineered for each individual vessel. It's a beautiful, elegant solution to a very powerful problem. So, we've established that the bulbous bow is basically a wave-cancelling machine. That's cool science, but what does it actually mean in the real world? Well, it means one thing above all else: incredible fuel efficiency. And when you're talking about ships that can hold over 200,000 tons of cargo and have fuel tanks the size of a house, even a small percentage of savings adds up to an astronomical amount of money and a huge reduction in emissions. Reducing that wave-making resistance we just talked about directly translates into less work for the engine. It's that simple. Think of it like this. Imagine you're riding a bike against a really strong headwind. You have to pedal super hard just to keep moving. The bulbous bow is like finding a way to magically eliminate that headwind. Suddenly you can maintain the same speed with way less effort. For a ship, less effort means burning less fuel. For large vessels like oil tankers, container ships, and modern cruise liners, a well-designed bulbous bow can reduce fuel consumption by up to 15%. That might not sound like a crazy number, but Let's put it in perspective. A large container ship can burn over 60,000 gallons of fuel per day. So 15% savings isn't just a few bucks. It's nearly 10,000 gallons of fuel saved every single day. Over the course of a year, that adds up to millions of dollars for a single ship. Now multiply that by the thousands of large ships crisscrossing our oceans every day, and you can see why this weird-looking bulb is one of the most important and impactful innovations in modern naval architecture. It's not just an economic decision, it's a massive environmental one too. Less fuel burned means fewer greenhouse gases and other pollutants being pumped into the atmosphere, which is a huge win for everyone. This is why you see these bows almost universally on any large ship that spends most of its time traveling long distances at a consistent high speed. That's the sweet spot where wave-making resistance is the biggest energy hog, and therefore where the bulbous bow can provide the most benefit. It's a perfect marriage of physics and economics. The initial cost of designing and building the bulb is paid back many times over during the ship's operational life, all thanks to the simple, elegant principle of cancelling out a wave. Okay, so saving fuel is obviously the biggest and most important benefit of a bulbous bow, but that newfound efficiency gives ship owners and designers a really interesting choice. When you suddenly make a ship more efficient, you have two main options for how to use that advantage. Option 1, you can keep the engine power the same and just go faster. Or option 2, you can keep the speed the same and use the extra efficiency to carry more weight. Both of these have huge implications for the shipping industry. Let's look at the speed option first. In some industries, speed is everything. For example, some specialized cargo might need to get to its destination as quickly as possible. Or for a passenger cruise liner, being able to cover the distance between ports more quickly means more time for passengers to enjoy the destinations. By reducing the drag, the same engine can push the ship through the water at a higher top speed. The power that was previously wasted making a giant wave is now being used for forward propulsion. So, if time is money, a bulbous bow can help you save a lot of it by just getting you there faster. But for most cargo ships, the second option is often more attractive, increasing the load capacity. The world of shipping is all about economies of scale. The more stuff you can fit on a single ship, the cheaper it is to transport each individual item. So, imagine you have a ship designed to travel at, say, 20 knots. Without a bulbous bow, the engine might be working at 90% capacity to maintain that speed with a full load. But once you add the bulbous bow and reduce the drag, the engine might only need to work at 75% capacity to do the same job. This extra unused power gives you a massive advantage. It means you can add more cargo, a lot more cargo, and the engine will still be able to handle it while maintaining that crucial 20-knot speed. You can increase the ship's displacement, which is its total weight, without needing a bigger, more expensive and more fuel-hungry engine. So the bulbous bow doesn't just make the ship better at moving through the water, it fundamentally changes the economics of how much that ship can earn on every single voyage. It's a classic engineering trade-off, and the bulbous bow gives you much better options on both sides of the equation. So we've covered the big ones, fuel efficiency and the speed versus cargo trade-off. But there's one more benefit of the bulbous bow that's less about economics and more about the ship's behavior in the water stability. Specifically, it has a noticeable effect on a type of motion called pitching. Pitching is the up and down, seesaw-like movement of the front and back of the ship as it goes over waves. If you've ever been on a smaller boat in choppy seas, you know exactly what this feels like. The bow rises up on a wave and then slams back down into the trough. It can be pretty uncomfortable, and on a large ship it can put a lot of stress on the hull. The bulbous bow helps to dampen this pitching motion. Because the bulb is a large, buoyant volume of space located at the very front and low down in the water, it creates an upward, buoyant force. When the bow of the ship starts to dip down into a wave trough, the submerged bulb provides extra lift, kind of like a cushion which slows the downward motion. Then, as the bow starts to rise up on the crest of a wave, the bulb, as it gets closer to the surface, loses some of its buoyancy, and its weight helps to counteract the upward lift, slowing the rise. This doesn't eliminate pitching entirely, of course. Nothing can do that in a rough ocean. But it does help to make the motion less severe and the period of the pitch longer and slower. It smooths out the ride. For a passenger cruise ship, this is a huge deal. A smoother ride means happier passengers who are less likely to get seasick. Happier passengers mean better reviews and more business. So while it might not be the primary reason for installing a bulbous bow, it's a very welcome side effect that improves the comfort and safety of everyone on board. And for cargo ships, reducing severe pitching is also important for protecting the cargo and reducing structural stress on the vessel itself. Constant, violent slamming of the bow into waves over a 20-year lifespan can cause metal fatigue and damage. By mellowing out this motion, the bulbous bow can contribute to the long-term health of the ship's structure. So, on top of saving fuel and increasing capacity, this weird nose also acts as a built-in shock absorber, making the journey better for the people, the cargo, and the ship itself. So, to wrap this all up, the bulbous bow is this incredibly clever piece of engineering that fights waves with more waves. By creating its own wave system that destructively interferes with the ship's main bow wave, it drastically reduces drag. This leads to massive fuel savings, up to 15%, which is a huge deal for the economics and environmental impact of global shipping. That efficiency can be used to either make the ship faster or allow it to carry way more cargo, all while giving passengers and the vessel itself a smoother, more stable ride by dampening that pitching motion. But you might be wondering, if these things are so great, why don't we see them on every single boat? Well, the key is that bulbous bows are highly optimized for a specific range of speeds and drafts. They work best on large ships traveling long distances at a consistent high speed, generally over 15 knots. This is the condition where wave-making resistance is the dominant form of drag. For smaller boats or for vessels that operate at a wide variety of speeds, like tugboats or ferries with many stops, a bulbous bow can actually be a bad thing. At low speeds, or when the ship isn't loaded to its designed draft, the bulb can create more drag than it saves, making the vessel less efficient. It's a specialized tool for a specific job. So the next time you see a massive ship with that strange-looking nose at the front, you'll know it's not a random design choice. It's a finely tuned, multi-million-dollar piece of fluid dynamics wizardry that makes our globalized world possible. It's a reminder that sometimes the most effective solutions in engineering are the ones that, at first glance, look the most counterintuitive.